aerodynamics. Let's take a look at how these forces work together to achieve straight and level, unaccelerated flight. This means that the airplane is not turning, climbing, descending, or changing airspeed. It should be fairly clear that before an airplane can fly, lift must be created. Lift is the upward force created by the effective airflow as it passes over and under the wing. Weight is the force that opposes lift and is caused by the downward pull of gravity. Thrust, created by the power plant, propels the airplane forward through the air, while drag, a retarding force, opposes thrust and limits the speed of the airplane. In unaccelerated flight, where thrust and drag are equal, the airplane will not speed up or slow down. Like thrust and drag, when lift and weight are equal, the airplane will not climb or descend. To help you understand lift, let's take a look at the basic principles of motion. In the 18th century, Daniel Bernoulli expanded on Sir Isaac Newton's laws of force and motion to describe the principle of airflow pressure differential. Observing what happened to air as it passed through a tube, Bernoulli discovered that as the velocity of a fluid or gas increases, its pressure decreases. He also found that with a constant velocity, the pressure of the air remains the same at both ends of the tube. If a constriction is placed in the middle of the tube, the same amount of air has to pass through a smaller area. This increases the velocity and decreases the pressure. If you were to replace the constriction with an airfoil, such as a wing, the same principle would still apply. As oncoming air meets the leading edge of the airfoil, it separates with part of the airflow going over the top and part going below. Since the air flowing over the top has farther to go, it must travel faster. The result is lower air pressure above the wing. This is a component of total lift. The remaining lift is provided by the downward-backward flow of air generated from the top surface of the wing. The lift provided by this flow can be explained by Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. The reaction to this downwash results in an upward force on the wing and an increase in total lift. Before we look at various airfoils and how they are configured to take advantage of the laws of motion and principles of lift, let's look at some of the terminology. A line drawn from the leading edge to the trailing edge of an airfoil is referred to as the chord line. The camber of an airfoil is the curve of its surface. On general aviation training aircraft, the upper camber is usually more pronounced than the lower camber. Any object moving through the air encounters a relative wind. This wind is always parallel to and opposite the flight path. The angle formed between the relative wind and the chord line is called the angle of attack. A way to measure lift as it relates to angle of attack is the mathematical expression, coefficient of lift, or CL, which is determined by wind tunnel tests and is based on the design of the airfoil. Each airplane has an angle of attack where maximum lift occurs. This point is known as CL max. Beyond this point, the airflow begins to separate from the wing surface, becoming so turbulent that the airfoil can no longer create lift. At this point, the wing is in a stalled condition. The amount of lift that a wing can produce depends on several factors. One of these factors is wing design, which includes the shape or plan form of the wing. A straight wing has good slow flight characteristics, but is not structurally efficient in terms of lift and drag. A swept back or delta wing is much better at higher speeds. The tapered wing, on the other hand, has good slow flight characteristics and has a relatively efficient design. Another wing design factor is the aspect ratio, or the relationship between the wing's length and width. The aspect ratio can be found by dividing the wingspan by the average chord. In this example, the wing has an aspect ratio of 9. At a given angle of attack, the larger the aspect ratio, the less drag produced for the same amount of lift. General aviation training aircraft, for instance, normally have aspect ratios of 7 to 9, while gliders are usually between 20 and 30. Another design factor that affects a wing's flight characteristics is the angle of incidence. In this case, the wing is attached to the fuselage with the chord line inclined upward at a slight angle. You, as a pilot, can control lift by changing individually or in combination the airplane's airspeed, its angle of attack, and the wing configuration, such as lowering the flaps. If all other factors remain constant, doubling an airplane's airspeed develops 4 times more lift. This increase, however, is not without its drawbacks, since any increase in lift also results in an increase in drag. In addition, with all other factors remaining constant, an increase in angle of attack increases lift. For lift to remain constant, airspeed and angle of attack must be used in conjunction with each other. If airspeed increases, you must